I want to say a few things about the Van Horn lectures before I turn it over to Professor Lewandowski, who is going to introduce our speaker for this year. I have a couple of pictures this year. I start with Frank Van Horn. So Frank, as most of you know, has a painting that appears in the library, but he's really a Renaissance guy. And one of the things I think is worth pointing out this year is connections, and I'll try and do that on a couple different ways, with respect to people and then also with respect to topics. So Frank came to the campus shortly after Case School of Applied Sciences began. He was the first faculty member in the geology department. He spent 26 years as the head of the Student Athletic Association. So the reason for this lovely sunset picture here is that field we walk by every day is Van Horn Field. And the magnitude of his investment is, part of it was his personal investment, is remarkable. So in 1900, he raised $155,000, which is a multi-million-dollar figure in today's numbers, in order to really balance against the scholarship, the well-rounded student, including the physical aspect of it. Something he shares with today's introducer. John is very active with the athletic department, as well as being a scholarly leader in our department. And then the third leg of this is the familiar library. So we don't do as much reading in that library now as we do defending things. So it's really a room where there is scholarship that's being added to the libraries of the world. This is where all the students ultimately will have a positive outcome when they're done defending their thesis. And so it holds a special place in really the collective experience that we all share. It takes us to the next generation because it was Kent Van Horn and his wife who created an endowment that allowed that library to exist. Kent Van Horn moved sort of down the supply chain from minerals to metals. So he got his degree in metallurgy at this institution, got a PhD at Yale, and then spent 2 years teaching at Yale, and the rest of his career was at Alcoa. It's interesting to me, at least, to see that he rose from research metallurgist to director of research, and he said he was a research metallurgist the entire time he was director of research. But when he was promoted to being the vice president of research and development, he sort of discontinued his role as a research metallurgist, which is an interesting confession or example of honesty on the part of somebody who really cares about the field. I have two of his books listed here. One is Aluminum and Iron and Steel. The other one is a collection of work from Alcoa that was written up by Alcoa employees and was edited by Kent. If you look in our library system, there's a complete set in the Cleveland Institute of Art and in the engineering school libraries both, which is an interesting connection. Arthur sort of shamed me last year by not bringing a copy of Practical Metallurgy. And so I can't outdo Arthur since his was handed to him by Kent himself. But I have a copy that's inscribed by the two authors, George Sachs and Kent Van Horn, to William Wickenden. And so Wickenden, you probably know, is the name of the building that's immediately next door here, just past Sears. But Wickenden also wrote a very influential report on engineering education that was published in 1930. If you go to an American Society of Engineering Education meeting in the year 2015, you'll still hear it referred to. And so this is another interesting connection. So between research, education, and then also practice. And so if I go one more slide through, I found an advertisement from, I think, Time magazine from 1960. This is a different picture of Kent. And so down here it says, Dr. Van Horn gets the green light. And the green light has two meanings. The first is the green light in the background. So in 1960, this is the fluorescent screen of the TEM that was installed in the research center over at Alcoa. So very early on, the value of these high-cost, rarefied tools was recognized, and the investment was made, and the investment was large. So everything I have over here is actually abstracted from here. But there's a couple of things. So this is 1960, just at the point, if you look at the use of aluminum, when there's an enormous increase in the use of aluminum here and around the world. And so the way this was done under the leadership of Ken Van Horn was to assemble a comprehensive institution heavily populated by PhDs, master's degrees, BS degrees, and a crack technical staff that supported them. The green light, the other meaning of the green light, was they got the permission to spend $30 million on the tech center. And if I plug this into the Google calculator for inflation, that's about $240 million today. So the investment in basic science was equally recognized, as much as education, as much as practical application. And the reason is this connection, that it is basic science that really underpinned all of the technical applications of aluminum. Without the basic science, aluminum would still be sort of a curio, I think is what it says down here somewhere. It used to be a curio. With basic science, you can turn it into something that performs in highly demanding engineering applications. So, the third generation is the lectureship. So the endowment from Kent created the library. The endowment was sufficiently substantial that the next generation of Van Horns, Neil and Karl, were able to set aside some of those resources in order to endow this lectureship. And it has been running since 1974. If you just look through the list, you'll see many names you recognize. We've had one leader in the field of material science and engineering after another come and speak to us and spend a long period of time and directly interact with the students. And that's one of the real other dimensions of connectivity that's treasured, I think, about this series. The last thing I would say about the family is that Karl continues to read all the letters that all the Van Horn scholarship winners write. Professor Matheson makes sure that he gets the grammar and punctuation corrected before we send him over. But he has a very strong connection to the first-year undergraduate students through direct interaction, and he has set aside a very substantial gift just this year in order to grow those undergraduate scholarships. So it's this multiple dimensions of connections that we always come to celebrate. I think you'll hear from Professor Lewandowski just how nicely this year's lecturer fulfills those sort of attributes.
Thank you, Professor Cawley. This is a real pleasure to introduce our first of the lecturers this year, Professor Harry Bhadeshia. But before doing that, I wanted to give you a little background on Professor Bhadeshia. He was born in Kenya to Indian parents and moved to the UK in the 1970s. He did his Bachelor of Science degree at the City of London Polytechnic in 1976, which is now known as London Metropolitan University, before moving up to Cambridge in the Department of Metallurgy, working with Professor Dave Edmonds and getting his PhD in 1979. He then did a SRC Research Fellowship until 1981 in that same department, and then joined the academic staff, and now is a fellow at Darwin College. I should note at that time, Sir Robert Honeycomb was the head of the department at that time. And in 2010, we had Professor Lindsay Greer, that you can see up here, which was the department head at that time. Well, as many of you may know, some of his earliest papers rekindled the discussion and debate on the bainite transformation. And there's been a thread of both fundamental and applied work connecting to some of the things that Professor Cawley said, practical metallurgy that has spanned his whole career. And so I went on the Web of Science quickly just to look at, some of these citations. And if you do that, it doesn't go back as far as I thought it would actually, but you'll see that the number of citations is obviously taking off very dramatically. And these first 2 years here, back in those PhD years, are some of those early papers on some of these fundamental aspects. Now, Thursday's lecture is going to come and cover some more of the recent developments in using these bainitic steels. And in particular, that's going to include other things that he's worked on that you'll hear about later on rail steels. And in this case, you can see here from a publication in the mid-1990s, where these bainitic steels are now being used in rails. Now, this has a lot of connections with me personally. First of all, the first rails were put in at the Derby station, apparently, as we read there, in the Midland Railway in 1857. So obviously I wasn't there then, but which is good. But I worked on fully pearlitic carbon manganese steels for part of my PhD thesis, as well as a number of other students. And in addition to that, our class on failure analysis has just been covering failure of some of these pearlitic rail steels. Now, we're not going to give this to Professor Bhadeshia to take back with him, but these new rail steels are really quite different in that regard, and hopefully much more fracture resistant. And so that whole field is beginning to change. Low carbon, carbide-free bainitic steels arose from some of this work in the 1990s. They're now used, if any of you have traveled in the Channel Tunnel or the Channel, or as you'll hear on Thursday, some of this more recent work for armor steels for the British military of defense. So all this work really points back to, in the connection to the department, there's been a long history of phase transformations work at Case Western Reserve. And you've heard a little bit about it already, but I want to give some more background on this. As Professor Colley pointed out, George Sachs was a faculty member. You may be familiar with a number of his orientation relationships. He also covered Kent Van Horn and the book that you just saw. A bit more recent, Al Troiano, perhaps best known for his work on hydrogen embrittlement, but also equally involved with early discussions on the Martensite transformation. Bob Heeman, also known as Bainite Bob, which Professor Bhadeshia remembers. Professor Hoyer's work on partially stabilized zirconia in ceramics. Professor Peruse's work on silicon and La-base phases, partly with one of our other Van Horn speakers, Peter Hazeldine. Professor Welsh on a range of metallic alloys, including titanium-based systems. Now, more recently, there's been work, as many of you are aware, on this very interesting phenomena of colossal carbon supersaturation in steels that the late Professor Gary Michael was intensely involved with, along with Professor Hoyer and Professor Ernst. A number of interesting phase transformations are happening in those systems, and that group has already heard some of your input on it. So let me return back now to Professor Bhadeshia. He's currently involved with at least 4 editorial positions. He's authored or co-authored 3 books and over 500 archival publications, and you could see the high citation list that I showed. The 3 books are called Steels, Microstructure and Properties with Robert Honeycomb, Bainite in Steels, and Worked Examples in the Geometry of Crystals. So obviously these efforts and successes do not go unrewarded on the national or international scene. In 1992 he won the Hume Rothery Prize, followed by in 1994 the Rosenheim Medal and Prize from what was then called the Institute of Metals. He was elected to the Fellow of the Royal Society in 1998, and followed that with, in 2002, a Fellow of the Royal Academy of Engineering. He's also a Foreign Fellow of the Indian National Academy of Engineering. In 2006, he became the Bessemer Gold Medal awardee, now called from the Institute of Materials, and in 2008 became the first Tata Steel Professor of Metallurgy. In 2009, he established and directs the SKF University Technology Center, and this has been focusing on bearing steels. And we have some distinguished guests in the audience that deal with bearing steels. Part of his talk today is going to cover work on computational metallurgy that he's been involved with for quite a while, but since 2005, he's been the professor of computational metallurgy at the Graduate Institute of Ferrous Technology at POSTECH. And he spends about 3 to 4 months there every year, has a separate research group there that's working on a number of these activities, and that's where he flew to us from and got to us about just before midnight on Sunday night. So like all of our Van Horn speakers on the list that you've seen, he exhibits an incredible stamina, which is impressive, a sense of purpose and drive. And so I wanted to try to capture this and relate it back to Van Horn a bit. And he shared with me, and maybe some others, that he took his Cambridge research group, which is now about 12 in number, on a bike ride. But the bike ride was no normal bike ride. It went from Oxford to Cambridge, which is about 91 miles, rather hilly. On September 27th, that's when they left, and they got to Cambridge on the same day. And they also raised money for the British Heart Foundation. But very interestingly, when I looked this up on the website, where they started that ride was at the Roger Bannister running track at Iffley Road, Oxford. And that was the site of the first 4-minute mile by Roger Bannister on May 6, 1954. Obviously, Van Horn's had quite an interest in academics and athletics, and that kind of completes the loop. So his seminar today captures some of this computational metallurgy that he's been involved with, both in his group as well as others. And it's entitled Extremely Complex Problems. We're really looking forward to it, Harry.
First of all, let me say I'm absolutely delighted to be here, and thank you all for coming here. And I've never met you in person, but we've communicated, talked about cats, about bearing steels, and so on. So thank you for coming today. This is Dr. Zaretsky, who was a pioneer in the creation of bearing steels for aircraft engines from a long time ago. And it took me several weeks to persuade him to write an article for a journal that I edited, but I succeeded in the end. Professor Corley, thank you very much for introducing the Van Horn Award and for inviting me here. And you know, I actually have a connection with Karl Van Horn because he is a fellow of St. John's College in Cambridge, and St. John's College actually founded my college, which is Dowing College. So without that, I wouldn't be here. And you know, Dowing College celebrated its 50th anniversary, so I wrote to Karl explaining that we've celebrated our 50th anniversary. So he wrote back saying that he recently helped St. John's celebrate its 500th anniversary. Okay? So these guys are really good. And John, I've learned a lot more about myself than I knew before. Very good. Thank you very much indeed. Okay. Now, you see a website over there, a lot of the details, including this presentation, available on that website for you to download. Okay? Now, I'm going to talk about extremely complex problems, and I'll introduce the first part of my lecture. I'll introduce the methodology. Okay? So it's a kind of like a tutorial. And the second part, I'll show you why using these methods is important. So a typical material science department will cover all of these fields. Okay? So you'll have device materials, which are, you know, electronic, magnetic, superconducting, and so on. You'll have physical metallurgy. You know, there's 1.4 billion tons of steels produced every year, which are extremely good and serving humanity without making any noise because they are so well designed. Then you have materials chemistry, corrosion, extraction, batteries, sensors, and so forth. Biomaterials, artificial bones, and slow-release drugs, and so forth. And polymers, ceramics, and composites. So material science is a truly interdisciplinary subject. You can be a mathematician, you can be a chemical engineer, you can be a physicist, chemist, as long as you are willing to learn other subjects. This is the subject you should do. But there are two themes which are common to material science. So we already saw Professor Corley explain, you know, the electron microscope that was installed in Alcoa back in 1960. Characterization features in all of material science. And characterization doesn't just mean electron microscopy. It could mean a very large fracture toughness test, for example, or, you know, rolling contact fatigue, and so forth. Characterization is key. And there is another subject which is key to all of these material science subjects, and that is mathematical modeling. Now, there used to be days, there used to be a time when it would take approximately 10 to 15 years before an idea actually made it into commercial success. That is no longer acceptable in industry. You have to actually take your idea and show that it's viable within something of the order of 5 years. You know, Rolls-Royce make aero engines, and they will not wait for you for more than 5 years to actually get something flying in the engine. Now, to do this, we have to reduce the timescales and the resources used to create new materials. And one way, and this is just a tool just like an electron microscope, is to use mathematical models to cover as much of information as you can so that you can get to your goal faster. And these mathematical tools now are quite common, and they form a part of the language even of undergraduate students. So, for example, this is a book which is quite a small book, and it's about introducing materials modeling. every single method that exists at the moment for doing calculations and trying to design materials. And in that book, we cover electron theory, molecular dynamics, thermodynamics. Irreversible thermodynamics is a subject between thermodynamics and kinetics. We have kinetics, which is a very badly behaved subject, finite elements, and the key aspect of material science is that we have structure property relationships. That is the essence of materials science. And given that we are not a pure subject, that means we don't treat a chicken as a sphere. Okay? We have to treat the chicken in the complex shape that it exists. We will have lots of uncertainties. And the treatment of uncertainties is an extremely important part of the problem. So you mustn't say that, I predict a toughness of 20.2 megapascal root meters. You've got to actually say, I predict a toughness of 20 point, well, I would eliminate the 0.2, 20 plus or minus, 10 megapascal root meters, and I think my mathematical model itself might have some uncertainty in it. Okay? So there are two kinds of uncertainties that we need to think about. Now, many of you will have seen this movie. This is a copyright-free slide that I got from the web. Okay, so the theory of everything, and that is the young Stephen Hawking and Janet, his then wife. And people in astrophysics and cosmology have the habit of really using very sexy titles for whatever they do. So, if the theory of everything has been solved, we could actually all retire right now, right? But if you asked Stephen Hawking to predict any of these properties, okay, he wouldn't have a clue on how to do it. Okay? Not only that, but nobody in the world would have a clue on how to predict something as simple, what we consider it to be simple, as a Sharpie toughness property. It's a completely empirical test, but it's widely used. No one can predict that. Similarly, the fatigue strength cannot be predicted. This is the fracture toughness, corrosion, even the simple tensile test. We cannot predict the stress-strain curve. Okay? These are extremely complex problems. So how can you design a material, if you can't predict the properties? Yeah? The engineer is not interested at all in whether you have GP zones in your material or you have a nanostructured material. They want to have properties with which they can design a component which will be safe over the service life that they calculate. So to summarize, all these properties can be measured. We have all the necessary instruments, down from looking at individual atoms to engineering scales which cover, kilometers of pipeline. Okay? And the pipeline has to be designed in such a way that if a crack starts, it doesn't propagate for kilometers. Okay? We can use these measurements, so all of these properties that I illustrated as an example, you can use them to make sure that your best estimate says that your engineering component will be safe over a certain design life. So we can use these measurements to estimate life, to control, etc. But if I gave you a comprehensive description of the material, that means the full chemical composition of a steel with 20 different solutes in it, and exactly how it was processed, and the details of the structure at whatever resolution that you like, you would not be able to predict any of those properties. Okay? So this is what I mean by a complex process, and I'll give you some example of that. So one advantage is that there exist vast quantities of data in the literature, really truly massive quantities of data in the literature. We need to do something to understand those data without simplifying the problem. Because once you simplify the problem, you lose the technology. Even the simple hardness test, so these are hardness indents. And when we teach about hardness, we say, okay, we make a diamond-shaped indentation, right? And measure the depth to which it penetrates the material. But actually the problem is far more complex. Okay, you can see that the region around the indent has been pushed up in a complicated way. So even to predict the hardness is not possible as yet as a function of all the variables that I illustrated. Now this is a steam turbine, and this is one of my former PhD students, Tracy Kuhl. And you know, this thing rotates at about 300 revolutions per minute. The steam temperature can be 600 degrees centigrade, and it's very long along this direction. It's got to last for something like 40 years. Okay? So, you know, to ask a question, how can I make this operate at 650 degrees centigrade and make sure that the materials will survive over that period is really tricky. You're not going to wait for 40 years to test your alloy. Okay? So we've got to have a method of dealing with this problem, and I'll illustrate some of the variables involved. So here we have complex chemistries where everything is added deliberately. I'm not illustrating impurities. Okay? Some of these elements are added in parts per million and controlled accurately. So boron, for example, is added in parts per million. So we have all these alloying elements which form our basket of things that we can add to the steel. There's processing involved, you know, rolling, forging, heat treatment, etc., multiple heat treatments before, after welding, and so forth. There will be different kinds of welding processes, and they will have their individual control parameters, and there will be final quality heat treatments. Quality is the term that they use for the final heat treatment, right? So I want to be able to predict the life of any of those components as a function of all these variables if I design a new alloy. How do I do that? Well, the first thing is I cannot simplify the problem. As soon as I simplify it and say, look, this is just an iron-carbon alloy, it becomes useless as a technological problem. Okay? And I'll illustrate that. So imagine this is an XY plot, and we've got a series of points over there. Those points look fairly random, right? Okay. There's no obvious logic to them. I'm going to now introduce a further two variables. One is the z-axis pointing out of the plane of the board, and this second is the time axis. And you'll see that the picture becomes immediately clear. If I actually had this movie operating with the z-axis pointing out of the plane of the board and time, then you would see that this is actually a man walking along the street. These are actually the arms and the body and the head. Okay? So by removing those two variables, this just looks like a random set of points which scatter. Okay? So if you simplify the problem, you basically lose the technological goal of the analysis. So how do we deal with this? Well, first thing is that there is no reason for anything to be linear. We have to have nonlinear functions, and we have to be able to deal with very large number of variables. So if you are modeling a rolling mill, there might be approximately 400 different variables. Okay? And a modern rolling mill actually has these models so that it automatically adjusts the conditions so that you get the right properties. This is extremely important. We need to deal with uncertainties in our calculations, and we need to exploit as many data as are available. So it's a very painful thing to collect all the data that are available, and in many cases the publications don't report all the data that you need. So you need to have a method to deal with missing variables. Okay, so the first thing that everyone is familiar with is an empirical equation. So supposing I'm trying to predict the strength of a material, I might write it as a constant times another constant times the concentration of carbon, and a similar term for the manganese concentration, and then for the nickel concentration. Okay? So it's a linear equation. These variables are assumed to be important, and we have also assumed that the problem is linear. So, you know, you present this to your supervisor, and he says, no, you know, I know that carbon and manganese interact with each other. So you go away and you treat the data again, and you introduce arbitrarily a product between carbon and manganese. And then if you have a bad dream, you might write the function like this. So the point is that given that this is a very complex problem, we don't actually know what relationship should model the problem. Okay? We don't know whether it should be linear, whether it should be nonlinear, whether it should include a hyperbolic tangent function, and so forth. So we need a method which automatically chooses the relationship. We don't specify it at the beginning. So this method is called a neural network. And when I was coming to the US on a previous occasion, the US immigration officer asked me, what are you coming here for? So I explained that I'm going to give a lecture on a neural network, and I thought I should explain a little bit more, which was a mistake, because I said, look, it works a little bit like the brain. And actually it's not at all like the brain, but neural implies something to do with the brain. So he said to me, I wish my boss had a neural network. Okay. Right, so here is a representation of that first empirical equation where we had the property, in this case toughness, as a function of carbon, yield, strength, and the phosphorus content. And I'm just going to represent that linear equation in terms of a neural network. So here are what's known as the input nodes. These are basically your input variables. In this case, the carbon, the yield strength, and the phosphorus concentration. And this is what we are after. We want to calculate the toughness, let's say. So I take the carbon concentration, multiply it by an arbitrary number, which we'll call a weight. I take the yield strength, multiply it by an arbitrary number. I take phosphorus, multiply it by an arbitrary number, add them all up here, and I get a value for toughness, which obviously will be wrong unless you're very, very lucky. Okay? So what you then do is you compare your calculated value with a measured value, and you modify the weights until you get a good match. That's basically linear regression. Okay? And linear regression is a subset of a neural network. So here we have our input nodes, output nodes, and the hidden nodes are where you do the multiplications and additions. And instead of doing this linear sum, I'm going to use a hyperbolic tangent. Okay? So hyperbolic tangents are very flexible nonlinear functions. So if I set the weight, the W, to a certain value, I can get it to behave linearly. If I set it to another value, it will behave in a different nonlinear way, and so on. And if I want to make it even more complicated, I would use two hyperbolic tangents so that I can map a function like this. Okay? So not at all different from the linear regression that I explained, but I'm now making it nonlinear using a very flexible function. Okay. Now, in the previous slide that I showed you, I had one hidden unit, okay, where I added everything up. I'll just go back to that to show you. Yeah, we have one hidden unit here. So we take carbon, multiply by a certain weight, and so on, and we add them up here. I can have a second function here, where I multiply by a different weight. So, and instead of doing a linear addition, I take a hyperbolic tangent of those products. And by using two hidden units, I can make the function more nonlinear. And this is exactly what we are doing here. So we are using two hidden units, two hyperbolic tangent functions, carbon multiplied by weight, take a hyperbolic tangent, yield multiplied by a weight, take a hyperbolic tangent, and so on, and two different sets of weights. So this is the equation representing that neural network, that our output is given by your input variable multiplied by a weight and some sort of a constant, just as in linear regression. And at the hidden unit number 1, you take a hyperbolic tangent of that summation, and you will do the same thing at hidden unit 2, and then you predict your output value of toughness. If it's not correct, you go back and you modify the weights. And just to show you how complex a function you can get from a simple combination of hyperbolic tangents, this is a movie which shows x, y, and z is our output. X and y are two variables, and I'm only using 4 hyperbolic tangents. And when the movie runs, you'll see how that function changes simply by altering the weight. So this is the same function. All I'm doing is altering the weight. And there are 4 hyperbolic tangents here. So you can see that I can make this surface sing and dance by altering the weights, right? So it's an extremely flexible mathematical function. And that's the reason for using the hyperbolic tangent. It isn't actually that I had a bad dream. And you can see that this is not a black box. Everything is explicitly defined in this equation. The complete description of the neural network is that simple equation. Okay. And this was the function that I was plotting. You can see there's 1, 2, 3, and 4 hyperbolic tangents, and all I'm doing is varying the weight, and the shape changes dramatically. Okay, so here's a question for you. I've got this set of data, and I've plotted 2 functions here. One is linear, and the other is that. Which one is correct? So you have to be brave and answer. Which one is correct?
The higher order polynomial is extracted beyond the data range, so that wouldn't be right.
Right. So
It depends on your criteria for matching, whether you use least squares or least to the power of 10,
okay.
whatever you choose.
So actually both answers are correct in the sense that I don't know the answer. I don't know whether the nonlinear function is correct or whether the linear function is correct. And I also need to understand what the consequences of that error bar is. In this case, the function is passing exactly through all those points. In this case, it isn't, and it still could be correct because we have some scatter, some error bars in the data. So how do I decide which is the real function, given that I have so many variables, I don't know what the function should be. If I have a neural network which is so flexible, I can make it pass through every single point with 0 error. Yeah? But, as you said, is this a correct extrapolation? Yeah, it could be, or this could be the correct extrapolation. So how do we deal with this? Okay, the solution is very simple. So I have data, and I split the data at random into 2 parts. Okay? One data set I call the test data, and one data set I call the training data. The training data are those which I use to create the function, and the test data to interrogate whether the function behaves properly. Okay, so here is what I mean. So the black points are the ones that I've used to create the model, and the white points are my test data, and I'm plotting here the error in the training and the test data as a function of the complexity of the model. Now here the model is actually too simple to capture the complexity of the data, because we are predicting these incorrectly, the unseen data incorrectly, so we get a high test error and we get a high training error. In this case, I've made the function pass through every single point in the training data, and therefore it behaves badly. It's overfitted because it behaves badly on the unseen data, so I get a large test error and a small training error, small or 0 training error. This is an optimum model because I minimize the error on the unseen data. Okay, so that way you can fix the complexity of the model by saying that, look, I'm not overfitting here. I've got a minimum in the error on unseen data.
Just a clarification. So training has confused me. So training implies change, but what that really is saying is how well does that line approximate the filled circles?
Correct.
Okay.
Yeah, so we are finding the coefficients, the W, for fitting the function and checking, how well does it fit those data points. And when it passes exactly through those data points, the training error is 0. Yeah? Now, here's another illustration. So, can somebody predict the next 2 numbers in the sequence? How about you? Since you are in the front desk, you're a good student.
Well,
Yeah.
I want to say 10 and 12, but you're probably going to pull it up and it's going to be like 491.
No, you're absolutely right. So next two numbers are 10 and 12. But they could equally well be 8.91 and 7.64, because this function here exactly represents the sequence 2, 4, 6, 8. Yes, so if I put 2 in here, I will get exactly 4. If I put 4, I'll get exactly 6. If I put 6, I'll get exactly 8. If I put 8, I'll get 8.91. And next one will be 7.64. So 10 and 12 are exactly correct, and so are 8.91 and 7.64. And if I show you the same thing on the plot, you can see that this is the linear extrapolation and this is the nonlinear function. And the only way to say which one is correct is by looking at unseen data or extrapolating and doing an experiment to validate that. So we've defined a new kind of an error. These are exact data, 2, 4, 6, 8. Yeah, they're exact numerical data. There's no error in those integers. But we are predicting here a large difference between two models. So we say that the modeling uncertainty is large in this region. The modeling uncertainty here is very small. So we have an error bar which represents the fact that we can use multiple models to represent the same data, but they extrapolate differently. So you do not have a danger of extrapolation, because you are saying, look, I've got this uncertainty in the models itself. Even if there is zero error in the experimental data, I've got a certain amount of modeling uncertainty. And that magnitude of that modeling uncertainty depends on the region in which you do the prediction. If it's here, then the uncertainty is small. Here, it's very large. And remember, we will have 200 variables. Yeah? So it depends on where you do the calculation in that variable space on how much of a modeling uncertainty you have. So this is not an error bar that we are normally used to. And here you can see that again. So I've got a set of data here and here, but nothing in between. And these three models extrapolate differently. So the modeling uncertainty is large here. And you know, frankly speaking, we are most interested in regions of the prediction where the modeling uncertainties are large. Because if they are small, then the knowledge already exists. Right? You really don't want to do experiments in the region where modeling uncertainty is small. That means you are not doing anything new. Yeah? Okay, now I'm going to show you a few examples. So this technique is incredibly powerful. Of course, it has to be handled with all the other knowledge that we have, but it's incredibly powerful in dealing with complex problems. It has even been used to find out which police person is likely to be corrupted in the future. Yeah? So not an ethical thing to do, but there are some correlations. Just today we were talking about oxidation and so forth, and this is a problem related to oxidation. This was in your group. So has the weight of a car increased or decreased over the last 15 years? Nope. A 15% increase in weight. And the reason is that safety regulations have come in. For example, you know, you can be hit from the side and still the passenger compartment has to protect you. And I had this experience. I was traveling by taxi to airport in order to go to Poland, and another car hit us from the side. Both of the cars were written off. Yeah, written off means, you know, not worth repairing. But everyone got out without a scratch. And the reason is, for example, if you open up the door, you know, you will find bars like this, which are very strong. And what they do is, if you get hit from the side, they transmit the force to the rest of the body, which in the process gets severely damaged, but you are kept safe. Okay? So you can see from the shape of this door that we need to be able to form the component, right? And yet we want it to be strong. And these are kind of contradictory properties. You know, that when you make something very strong, generally speaking, the ductility decreases, and you don't really want to join things up to make such a complex shape. You should be able to form it from a simple sheet material. So the problem is that we want to make things strong, and yet we want to make them ductile. And one method, which was the name TRIP, comes from the US, where, now who was it? Parker, Zecke and Parker, that's right. They did some experiments on fully austenitic steels, and when they pulled them, they found extraordinary ductility. And the reason is that phase transformation happens under the influence of stress, and that phase transformation causes a change in shape, a shape deformation, which is a small addition to ductility, but more importantly, it adds to work hardening capacity, and therefore you do not get a plastic instability early in the deformation. If you don't get a plastic instability, you can stretch it much more. So these alloys are too expensive for normal use, you know, something like 30% nickel. But this is a very, very clever alloy in which you produce austenite, which will transform under the influence of stress or strain into martensite, but incredibly cheap, using carbon as an alloying element. Now, you can't use a large carbon concentration because you have to be able to weld these things. There's approximately 3,000 to 5,000 spot welds in every car. Okay? And if those do not pass rigorous tests of fatigue and so forth, you know, your steel will not be used. Simple as that. So notice that the carbon concentration is very small. So how do we stabilize the austenite? You know, if I quench this material, it would transform completely into martensite. There would be no austenite left. So what they do is they first form about 70% of ferrite at a high temperature. When the ferrite forms, it partitions carbon into the rest of the austenite. So even though your average carbon concentration is 0.15, the concentration in the austenite is much greater. And you increase it further by transforming at a lower temperature into bainite, which also partitions carbon. So you end up with about 1.28% of carbon inside the austenite, even though the average is 0.15. You can't get a cheaper alloying element than carbon. In fact, during steel making, you remove the carbon from the iron that comes out of the blast furnace. So this is called a trip-assisted steel, and it has a very simple composition, and notice the silicon. Now, as Professor Lewandowski said, you know, bainite is my favorite topic, and I've worked on it for about 40 years, and I'll summarize all that in one slide here. Okay? So basically, it forms exactly like martensite, right? So it's a diffusion-less transformation, but it's forming at a temperature where the carbon is mobile. So shortly after transformation, it escapes into the remaining austenite and then precipitates as carbides, iron carbides. But if we stop this reaction here, then we end up with a mixture of ferrite plates and carbon-rich austenite. And the way to stop this reaction is, this is the cementite unit cell, Fe3C. If I pull out an iron atom and substitute it with silicon, then you can see that the energy goes up dramatically. Cementite hates silicon. Okay? So if you add a small amount of silicon to your steel, then cementite will not precipitate in these circumstances. So the role of silicon is basically to allow us to produce austenite, which is rich in carbon, and not to lose the carbon by precipitating cementite. And the second thing about this bainite reaction is that there is a shape deformation. So this is an atomic force microscope image where you take a crystal of austenite, you polish it completely flat, and then you allow it to transform into bainite. Then you get these massive deformations, which are good for work hardening. And work hardening prevents plastic instability. Okay? So these are called trip-assisted steels because the amount of austenite is quite small. It's about 15%. And it's produced by this partitioning of carbon. But as your wonderful student pointed out, there's a problem, you know, that silicon forms an oxide during the processing, which is called phthalate, here, Fe2SiO4. And that can be liquid at your temperature, heat treatment temperature, so it penetrates the steel and locks itself to the steel. So when you come to remove the oxide by the processes that I have in the steel industry, you are left with some remnants of this iron oxide because it keys with the phthalate. And that iron oxide then oxidizes to a red colored oxide, which is unacceptable just from looking at the steel. But it's even more unacceptable when you go to coat it with zinc because it doesn't wet at those points. So we don't really want any blotches on the surface, external surfaces of a car body. Yeah, you wouldn't buy it. So how can we solve this problem? Well, there's an awful lot of variables in producing this steel, and I'll just show you the properties that we are after. So if I take all kinds of automotive steels and I plot the strength and the elongation, so this is the elongation, which is important in formability, and this is the strength, you get the so-called banana plot. Yeah? That as you increase the strength, your ductility goes down. There are some special steels which are called twinning-induced plasticity steels, which are rich in manganese, which have a higher combination of strength and elongation, but they are actually very expensive. So we have these large gaps here, and if you can fill those gaps, then you would become rich. Now remember that you're not simply going to look at elongation and ultimate tensile strength. There are so many properties that have to be satisfied before a car manufacturer will accept your steel, but I'm keeping the story simple here. So in producing trip-assisted steels, you have many variables, but these are important ones. So you have chemical composition. You can't add expensive elements here, okay? And then you have a complex heat treatment. This heat treatment is to produce the ferrite at high temperatures. This is to produce the bainite at low temperatures. And we require a certain amount of retained austenite. We require a certain amount of strength. And we require a certain amount of properties. So this is ideal because there are thousands of papers on trip-assisted steels where people have varied many, many things and produced good experimental data. So we collected those data and created a neural network model asking the question that, look, I do not want a silicon concentration more than 0.5%, but I want the following properties. I want a certain amount of retained austenite and certain elongation and certain strength values. Find me a steel composition. So you connect the neural network to something called a genetic algorithm, which basically tries out many, many different values of these variables and looks at whether you are within the acceptable range, and then finally gives you a set of answers. We came up with a really bizarre prediction, and we made the alloy, and it had this structure, which is totally different from anything that exists in trip-assisted steels. This looks like, so if there are Chinese people here, this looks to me, if you look in distant focus, it looks like Chinese script. Yeah, do you agree? Little bit? Okay. So what's happening is that these are actually dendrites of delta ferrite. So this is delta ferrite is simply the ferrite that forms from liquid. Okay? And this is your austenite, which we can transform into bainite or whatever we want. And the chemical composition that was predicted is as follows. So it's actually saying I can achieve all those properties with high carbon concentration, 0.48% carbon. And remember that we have variables which control spot welding in the model. And silicon, we obviously force the model not to have more silicon than 0.5%. And it's increased the aluminum concentration to 2.8%. And when we did a phase diagram calculation for this, you can see why we have that delta ferrite. the alloy can never become fully austenitic. Okay? Now that's an advantage. It doesn't matter whether we have delta ferrite or ferrite produced at low temperature. It's ferrite and it will partition carbon as we want. Furthermore, if it never becomes fully austenitic, it can never become fully martensitic. So when you spot weld, you have very rapid heating and very rapid cooling. So if you have a high carbon concentration, you get brittle martensite forming. But if you cannot form 100% austenite, you cannot form 100% martensite. That has to be good for spot welding. Now, the way that you work with mathematical models is that you make some prediction, and there are uncertainties. So you do not make a large quantity of material. You first make about 60 grams of material to validate your prediction. And if it's going roughly in the right direction, you make a larger casting. And of course, when you make these castings, the compositions won't be exactly correct. This is the constitution. So there's about 80% total of ferrite. And then we end up with the remaining liquid solidifying into austenite. And this is now the recalculated phase diagram for the actual alloy that we made. And we then heat treated this alloy to produce bainite in the regions which are austenite. So it looks slightly different here. Okay. So this is the very first alloy. There's no making 10 alloys and choosing. Okay. So we have the bainite and retained austenite here, and this is the delta ferrite that is unchanged from the solidification. And the very first alloy produced incredibly good properties. So for an automotive steel, this is a very high strength, 1000 megapascals. Okay? And you have uniform elongation of the order of 22%. Uniform elongation is what matters, not what happens after plastic instability. And if I measure the retained austenite content at the beginning, it's the correct amount, 15% I mentioned earlier. And as a consequence of deformation, some of that transforms into martensite, and that leads to work hardening, which you can see here. And we seem to have almost the right amount of work hardening. That means, if you have work hardening which is very steep, it gets too strong, and then it will break. Okay? You want a curve which is something like this, where the austenite transforms gently. Now, to prove that it's the transformation of the austenite that is helping us get this elongation, we did this tensile test at 100 degrees centigrade. Now 100 degrees centigrade doesn't do anything to the microstructure because it's produced by transformation at about 400 degrees centigrade to bainite. Yeah? But it alters the stability of the austenite to martensitic transformation. The austenite becomes more stable. So if the austenite doesn't transform, we should get a lower elongation, and that's exactly what happens. So here is the test done at 100 degrees centigrade, and you can see the austenite is not actually transforming. Yeah, so it's the transformation of the austenite that gives us the elongation. And if you look at all the commercial trip-assisted steels, this is the alloy obtained the first go, okay, from the prediction to making a small melt. And then, of course, there's a lot of other work to be done to measure weldability and hundreds of other parameters. But that gap that I was telling you about is filled. Okay? And furthermore, the addition of aluminium reduces the density of the steel by 5%. Okay? So the specific strength is even higher. Yeah? Yeah.
What would be a grain size in these types of alloys?
Yeah, so
Because your delta ferrite is...
yeah, it's there you go. Yeah. So it's not particularly fine, but we have the austenite and the bainite and then the martensite distributed throughout the structure, which gives the strength. Yeah. Okay. Now, this is a fusion reactor, and the current one that is being built in France, an international project, there will be approximately 200 displacements per atom during the lifetime of that process. So if you have a material in there, every single atom is displaced from its position 200 times during the lifetime. Just imagine that. Okay? So that is a damage level which is far greater than in a fission reactor. Okay? But we do not have any knowledge about materials behaving under these circumstances, and there is no experimental facility in which you can expose the material to 200 dPa of damage. And yet, you know, we are going to spend several billion pounds in making this reactor. Okay? So how do you cope with that? In this case, you have absolutely no choice except to do some kind of modeling. Yeah? And you do modeling on the basis of the data that you have, which is from the fission program, where the dPa at most goes up to something like 30 displacements per atom. But the point is that in about 5 or 10 years' time, there will be an experimental facility which is not a fusion reactor, which will allow very large doses of radiation. But the volume of material that can be exposed to that is quite small. So if you want space in that volume, it's like sending a sample into space to do an experiment. You have to really, really justify that you've done your thinking to do that. So the aim was to model irradiation hardening, okay? And there is currently no theoretical model which can do that, okay? Because the problem, again, is extremely complex. There are data collected, vast quantities of data, because in the nuclear industry, of course, you are very systematic in keeping data. Yeah? And we have 1,800 data which go up to 90 displacements per atom with 36 input variables, but they do not include any heat treatment information. But we know the chemical composition, and we know something about the properties. So the lack of information on heat treatment is a major, major shortcoming of the scientists who have worked on this problem. You know, if you had asked any metallurgist before collecting these data, they would have said, you know, heat treatment should be included in reporting your results. So the idea is we want to do experiments in regions where data do not exist, okay, because there's a limited amount of volume that will be available. So we worked on this, and here I'm plotting the yield strength increase as a function of the dose per atom and as a function of temperature. And you can see that irradiation would produce a huge amount of hardening, which will cause problems with toughness. But the more interesting part is to look at the uncertainty. Okay? So this uncertainty defines where we need to do experiments. Okay? So the purpose is not really to predict the hardening, but to predict the regions of that complicated input space of 36 variables where experiments are necessary. We don't need to do experiments in this region where the uncertainty is small. Okay? So we are using this in order to define where the experiments are necessary. Now, going back to this problem of the steam turbine, okay? In order to get greater thermodynamic efficiency, we need to raise the steam temperature to beyond 600 degrees centigrade, even 700 degrees centigrade. There is no steel, no ferritic steel capable. So we tried very hard to develop a ferritic steel. There were major international programs to do this. They really haven't been successful. Yeah? And if you use an austenitic steel, you can get there, but the thermal expansion coefficient of austenite is too large. It causes thermal fatigue and other problems. Okay? So what do? Well, we have creep-resistant materials which are used in aircraft engines at 1400 degrees centigrade. Okay? So, you know, these blades here are nickel-based blades, single crystal blades, and they are used in an environment which is at 1400 degrees centigrade, and they are rotating at, you know, 25,000 RPM. But the cost of this material is incredibly high. Yeah, in an aircraft engine where you use small quantities, that's fine. But you could not possibly use this for application to a steam turbine. So the idea is we need to downgrade this material, remove all the expensive things, because we only need a temperature of about 700 or 750 degrees centigrade, not 1400 degrees centigrade. So again, we have a very large quantity of data, and we designed a steel using the neural network, not a steel, but a nickel-based alloy. And this is the composition we came up with. Notice there is iron. Iron is not good for nickel-based alloys. But if you allow iron to be there, then the price goes down because you can use scrap material. Okay? And various, it's a much simpler composition than any nickel-based alloy that goes into the aircraft engine. There's no rhenium, ruthenium, and so forth. And we call this alloy FT750DC. FT is for Frank Toncre, who was my postdoc who worked on this. 750 for 750 degrees centigrade steam temperature, 100,000 hours, 100 megapascals stress. And DC for dirt cheap. Okay? Yeah. So, this is the microstructure. We have a small fraction of gamma prime. You know, normal aircraft engine alloys contain almost 70% of gamma prime. And we are interested in the yield strength as a function of temperature. These were the predictions, these are the uncertainties, and these are the experimental results we obtained. And similarly, for the creep rupture test, we've gone up to approximately 10,000 hours. These are the predictions, this is the requirement, okay? And these are the uncertainties, and these tests are still continuing. And there are many examples like this, where at the first go, you roughly reach the right composition. And then, you know, there's a lot of work to be done to make sure that you can manufacture it in large quantities. So we go from 60 grams to 100 kilograms and then to 9 tons of material. Now, there are a lot of people here working on fatigue, including different variations of fatigue, like the rolling contact fatigue. But this is not about rolling contact fatigue. This is about fatigue crack propagation. And we created a neural network model which has these variables. No chemical composition, no heat treatment. Okay? So this model should apply to anything, even though it was created on data on steels. It should apply to any material. So let's see if that works. Because, you know, you could argue that the composition and the heat treatment are embedded in these variables, which strength, elongation, and so forth. So this is steel being the model being tested on unseen data. Okay, so this is the threshold fatigue crack growth intensity, and this is the Paris law region. You apply exactly the same model to a completely different alloy system. So none of these data are included in the model. This is now nickel alloys, and you can see that the predictions are pretty good. Yeah, because the variables are, you know, that influence the fatigue. What this says is the variables that influence the fatigue are captured in the input variables that we chose. And here's titanium alloys and aluminum alloys. Okay. So I'm very impressed by this. So there are many, many other examples. And there's a review article that I wrote in 1999, which you can download from the website, which shows a vast number of subjects using this method in order to simplify complicated problems. And that, I think, is my last slide. So I'll be happy to answer questions.
Thank you.
Okay.
Well, we do have time for a number of questions, so we would like to begin. Mr. Paul.
Well, okay, I've got a sort of a question about how you add complexity. So you have a function within the argument of the hyperbolic tangent, and then you have the summation of the hyperbolic tangents.
That's right.
And how do you choose whether or not to add complexity to the argument or to the summation?
Yeah. The argument only has weights.
Right. So they're just constant coefficients?
That's right. And the hyperbolic tangent, the number of hyperbolic tangents that we add, gives you the more and more complicated functions.
And so the uncertainty, like with the one that you got the interpolated region, so the question that you're asking is, I have a large number of
models that equivalently fit the data I can see.
Correct.
So there must be a criterion for equivalence of fit.
Yes, there are two kinds of errors. One is that if you repeat the experiment, you get a different answer because something is not monitored. Okay, so you mustn't fit to a greater degree than that noise. And the second kind of error is, all the models that are able to reasonably represent those noisy data, how do they behave in regions where there are no data?
I think I'm asking a simpler question though. If you have them that fit equivalently where you do have data, how do you decide what's equivalent?
Simply that we haven't fitted any of the models to a noise level below the noise in the experimental data here. Yeah.
I'm very curious about that microstructure you showed. So, where are the grain boundaries in that?
So at high temperatures, you get precipitation of delta ferrite dendrites from the liquid, and then the liquid solidifies to austenite. The remaining liquid solidifies to austenite.
But it seemed like you have islands of austenite.
Yeah, that's absolutely right. And then as you cool, that austenite transforms to martensite. But when we do the heat treatment, we can get the austenite to regenerate and then transform partly into bainite. So the boundaries are between the delta ferrite, the austenite, and the bainite.
So it's the austenite transformation is from the liquid phase and not from the delta itself.
Well, there might be some from the delta, because if you look at the phase diagram, it's got a curve like this. Yeah?
Professor White.
Harry, could you compare the same alloy we're talking about to the quench and partition? This whole approach using Q&P that has been pioneered by the Colorado people.
That's right. So on the graph that I plotted all the automotive steels, which includes the quench and partitioning data. But their steels are actually stronger, so they're on this side.
Yeah, I thought that the criterion was to get to 1.5 GPa.
But even 1,000 megapascals would be very good, because you don't need high strength everywhere in the body. So for that bar, you don't need formability. But for the actual car body, 1.5 would be problematic, because when you're forming, you get springback, which is quite severe. So the forming operation, so springback means you form a material, because it's very strong. When you remove the die, it deforms elastically. So high strength, very high strength, has problems in areas where you want to do other things. So they all have their applications, actually.
Are there any other questions? Yes, some student questions.
Yeah.
Fantastic.
So I do like the name of your dirt cheap alloy, but so it's undoubtedly cheaper than current generation superalloys, but how does it compare to some of the early generation ones, both in price and performance?
I think you can find other alloys, but they're not really designed for very large scale objects. So here we also consider segregation. When you make a large casting, you will not have uniform composition and so on. And the price that I would compare against is steels, and it's far more expensive than steel. But you don't really have a choice if you want to go to 750 degrees C steam temperature.
Other questions? Yes.
I think I missed some part of your presentation. Is that remaining austenite and bainite doubly responsible for the tripping mechanism?
Yes, absolutely. So it's that small amount of austenite, the 15%, which trips and causes work hardening. So it trips in regions where you have a stress concentration of some sort, and therefore it hardens that region, and so you don't get the instability too early in the process. Yeah.
Professor Rams.
How do the neural networks actually deal with uncertainty in the input? If you wired this network up to the Cleveland casino, say, you feed in the day of the week, the weather, And can you predict what comes out of the roulette table?
So there are certain things that you can't do. Yeah. So for example, you can't model periodic functions with the neural network. Yeah. I don't know whether you can model a random event.
But there is a certain randomness given by the uncertainty of measurements.
Right.
So how does that interact with this neural network?
Yeah. So any uncertainty in the input will be reflected in the uncertainty in the output. So these are the two error bars that I was talking about. One is modeling uncertainty and one is the noise in the data.
So that's just empirical. You don't have an analytical control of that, or do you?
We can stop the model from fitting below the noise level that we know about in the data, because then it's just overfitting. It doesn't make sense. Yeah.
Yes.
Actually, to me, it looks like the neural network is kind of reliant on training.
Yes, absolutely.
Okay, so it means if you really have like unknown component in the system, then there's no way you can really kind of predict instead of really like after the training you do this and with uncertainty, right?
Every single example I gave you is a prediction. That knowledge did not exist.
Mm-hmm.
Yeah.
But you still need some training, like you have to have some idea beforehand, like you have to know that this kind of material has a certain range.
Yeah. So not only do you need the data, but you also need to use your experience. You know, supposing it told me that you need 10% of carbon, 10 weight percent, I would not accept that result. Yeah.
Because what occurs to me is I'm thinking about the high entropy alloys. So basically, it's to me, it's like a random mix, and it works out pretty good. So is your model capable of predict any new elements?
So not my model, but another person's neural network model, because I don't work on high entropy alloys. But watch the next issue of Material Science and Technology, which has a special issue on high entropy alloys, and I've written an editorial in there where people use the neural network model and actually made predictions of 4 alloys, which worked out to be single solid solutions. You know, high entropy alloys, they are after single solid solutions. Yeah.
Yes, please.
Okay, so I think everyone in this room has probably held a book written by former Van Horn lecture speaker I know now, Michael Ashby.
Mm-hmm.
And so you spent a lot of time today talking not just about Bainite and steels, but also just general methods and new approaches to neural networks and the testing that you were showing with the training. And so do you think there's something about Cambridge which causes the material scientists there to develop new approaches or new tools for the toolbox?
But Ashby is not a material scientist. He's a professor of engineering.
I think I've seen really good work here as well. You know, in English we have a saying that, you know, because we live in houses and we have gardens on either side, small gardens, and fences between the gardens, the other man's garden always looks greener. Yeah? But I saw really nice work going on here as well, you know. In fact, I told the students that it's breathtaking, some of the work. Yeah.
Earth, are you ready for a question?
I had a very interesting. I have one question. Most of the variables that you're talking about, at least the strength variables, etc., are really not deterministic. They're probabilistic. They have some type of statistical distribution. Is that accounted for in your knowledge?
In the sense that if we have missing variables, then there will be scatter in the data. And that scatter is captured in the noise. Okay. Yeah? So whenever we repeat an experiment and get a different answer, we haven't controlled some variable.
Well, because I relate back to the rolling element fatigue. You have a distribution exponential in that type of data. Other data, as an example, fracture will be beyond normal. You have very little scatter data. So it depends what type of experiment and what type of material.
Correct.
And so the question, it's really a rhetorical question. I don't want to put you on the spot. You're really designing for a given probability of survival or for correctness as opposed to a deterministic value that you expect to get.
you must always quote the uncertainty in prediction. Yeah, but you know, if there is scatter in your data, unfortunately, we usually don't have time to investigate why, but there is some variable which you are not monitoring.
That's a good question.
That's the French.
So, not so much on the metallurgy side of this, but more on the language. And you know how somebody mentioned to me today that artificial intelligence, people are trying to get rid of that word and replace it with deep learning because the word sort of is a blocking word. And I've sort of always had that idea about neural networks. I mean, we've heard about them for a long time. But that's just a technique. I mean, there's many other techniques. And so that parametric fitting or wisely applied parametric fitting is the technique you're doing to fit models to data with a sense of how much information content you have.
So you are absolutely right. There is no artificial intelligence here. It's a simple mathematical function. And you know, the name itself is not one that I have chosen, but you know, it's like in cosmology, where they will call something dark matter when they don't understand it. So neural networks have no relationship to the complexity of the operations that go on in real neurons down there. Yeah, in fact, we don't understand how that works. But that's the name we are stuck with. The advantage of the method is you don't need to specify the function before you start creating the model. The function is discovered.
Don't need to, or you did with your hyperbolic forms, and it's just flexible enough to take any shape.
Yeah, so
you actually did specify a function.
Well, it's arguable because I didn't specify the weights, so the function can be, yeah.
So that part, I mean, it's a general class of parametric fitting. And so I would be interested to see if there are advantages to using neural network methods. So in our group, we use structural equation modeling.
Right.
So I used, and there's a whole bunch of these network models, and your class of problem is a network model.
I think you're absolutely right. And you should regard this just as one tool in an armory of tools.
Yeah. Professor Matheson.
So I'm wondering with this, lack of better word, this neural network method, before you get to the summation, I mean, if you've got 240 variables, some of which you know very well, and some of them you don't know very well, but it may not matter in the error prediction that you don't know that very well. And so I'm wondering if you can probe the model in situ to find out where we need better experiments.
Yeah. It's an excellent point. And there are other things we can examine in this. For example, how much does this particular variable influence variations in the output? And you know, if it is insignificant, you could actually just remove it. But when you start the process, you put in as many variables as you can find.
Sure.
Yeah.
That would rely on the assumption that this variable is independent of others.
Yeah.
That can be misleading, of course.
Yeah. So for example, in the chemical composition, if you also specify iron, then that's not an independent variable because it's 100 minus all the others, you know?
Yes, please.
In your neural network, for a given fitting, how many different functional forms would it consider?
So that's a very good question. So we actually form a committee of models, yeah? Because there's an optimum size to a committee. If you have, it depends on the problem, but if you have too few members in the committee, then that might not give a good result. If there are too many, that might also, and we find the minimum in the test error for the committee to design how many members there should be, how many different models we take an average of to get a prediction.
Are there any other final questions? Well, this has been an excellent start to the Van Horn series. We just want to thank you.
Thank you very much.
And we are going to present a plaque which reads, the Case School of Engineering, Department of Materials Science and Engineering of Case Western Reserve University honors Professor Harry Bhadeshia Van Horn, as its Van Horn Distinguished Lecturer for 2015 in recognition of his outstanding contributions to the science of materials. Thank you very much. So is there a young person?